And the idea here is you have a reference for your class. So if you need something repeated, you can go to that channel and I'll provide you the link of when I get it uploaded. And you can look at it, you can scan through it, do whatever you need to do with it, but it is your class for it. So if you find something that's still a little mystified, I guess you could say, then please, by all means, give me a chat. I am normally on Discord from about 6 o'clock in the morning to about 8 at night. Now, I'm sure every one of you are gamers, right? Who isn't a gamer, I should ask. So we got all gamers. All right, Owen, what do you play? Okay. Peebles, what do you play? What kind of games do you play? You know, video games. Okay. Wonky? Okay. Yan? Okay. Jurassics? You cut out. Okay. How about you, Matt Zach? Okay. Okay. Wheeler? Okay. I can understand building computers. I've built mine. Hefty price tag. Go ahead, Owen. Okay. While he's disconnecting and reconnecting, the reason I ask you about gaming is everything that we go through, everything, okay? Everything that we go through in this block has an association with what your game is doing. Everything from the time that you are using the controllers online, and this has everything to do with online, with everything that you're doing with your controllers to what happens on the distant end and when it gets back to you. One of the worst things I hate is high ping rate. And especially if you're playing like on the European server, the Russian server, or the Asian server, it becomes an issue big time. But I know the problems with it, so I will only play those sporadically. So that's the reason why, if you want to, how would you say, sharpen your skills when it comes to gaming, start playing the overseas servers. That way you get a different taste of how they are playing their characters and that, but you still have that high ping rate. Now we'll go through some of this and I'll try to associate it with it. And high ping rate for me when I'm playing World of Tanks, I'm not a big fan of War Thunder because it's too fast for me. I'm kind of slower. Mine is solely PC. I'm not very good with the controller. I just like the keyboard better. And yes, you can attach the keyboard to like the Xbox and the PlayStation. Just not a fan of it. So when we are looking at this, we got to tie everything that we need to know about something called timing. Now timing is, and this is the objective here, identify basic facts about timing and synchronization standards. At any point that you've got a question during our instruction, please ask it. I do like to hear some stories that you might have that would relate to that. But I have my own stories, and I'll try to keep this quick and easy because we have This morning session, I got to get to a certain point, and then we have the afternoon session, and I got to be at a certain point, which is 2 alpha, finishing up, so you guys will know what you're doing when you get in your first lab. Which reminds me, does anybody have the capabilities of being able to send the lab time frames to me, please, so I know what days to fit in things like homework and appraisals that we go over? Anybody want to volunteer and send that to me? Okay, really appreciate that. That way I try to fit in my instruction in between your times where I'm not interrupting what you're doing at the lab sessions. There are some times, because you got a very small class anyway. What, 8? 1, 2, 3, 4, 5, 6, 7. 7, wow. Not used to this. I'm normally seeing between 10 to 12 students. Okay. Are there any other questions for me out there before we really get into it? Okay. Okay. Here's what I'm going to suggest. You send me the time that you're going to be at the dentist, and we'll work around it. Not just send it in, do the at symbol, Mr. Mayor, and send it to me, because you don't need to tell everybody else when it is. We can just work around it. Make life easier for everybody. And again, if you've got a particular thing that you have to do, like a doctor's appointment like that, that's a little bit different. But anything outside of that, you're supposed to be in this classroom. If you want to call it a classroom, it's more of a virtual classroom than anything else. All right, we're going to identify basic facts about timing and synchronization standards. I do ask questions, so if you're going to go to the bathroom and come right back, just type in the BRB scenario. Now, I do know what that means now, because even though I'm old, I still try to keep up with what you guys are. And thank you, Ying, for sending it to me. Okay, so just to give you an idea, this is one of the bigger tests, and it is what I classify as a college test. It is tough. So if you are not looking at information and trying to go over this information every day, either building flashcards or anything to that nature, studying however you want to study, this is a lot of information on this particular block. And everybody will probably tell you that it is not an easy one to get 100 in. So without further ado, the test that we are looking at, we're going to get it's a 40-question test. You have to get 28 of them correct to get a 70. I would suggest that you try to go a little bit further and not try to skim on the top there. With this in mind, we always have an AFSC application. Bottom line is you're going to have to deal with timing, and that includes every piece of equipment that you touch, because there is a timing source in there. We're going to look at purpose of timing, time standards, timing sources, time coordination, distribution agencies, timing jitter, and network synchronization. So when we look at these things, we're dealing with multiplexers, satellite terminals, radios, phones, internet, routers, gaming systems, you name it, we're dealing with it. But it all comes down to it uses time to do it. Time in frequencies. You guys have heard of phase lock loop. There you go. We got to keep it on time or on frequency. So this particular picture shows you a scenario that I have seen and have used out in the Air Force. But we have what's called a multiplexer, which is in the center. This is an old FCC 100. We don't have it anymore in the Air Force inventory, but we give you this picture to show you any multiplexer could be in there. You notice that we have a nipper net, a sipper net, and a local switchboard. Now these are all channels going into this multiplexer. This multiplexer in this particular scenario has 16 channels, but nowadays we've upgraded to at least 24 and more. With the multiplexer, it's going to combine all these signals together to give us one aggregate. You're going to hear a lot of that aggregate, and it's using timing to keep everybody on time. So we send it out to the satellite system, send it up to the bird in the air, it gets repeated back down to Earth to another place, and then they demultiplex it into the different users as to where it goes. There are time standards. We have apparent time, mean time, atomic time, and coordinated universal time, not to be confused with hammer time. Dun, 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 dun. No? No? Bad pun? Okay. So the first one up is apparent solar time. This is basically the history, the way we like to look at it. We always start with a little history and work our way up to what we really need to know. This is a sundial. But the problem you have with the sundial is 12 noon every day does not equal what the sundial is telling you. Why? Because you have the Earth axis, we have different seasons, we don't go in a circle orbit, it's elliptical. It is the least accurate time, but it gives us a sense of time. So we look at mean solar time. This is where we go through the history and start looking at, oh crap, watches. That's when it starts coming into play. But I always like to relate to something everybody should know, which is in London, England. You guys have ever heard of Big Ben? Okay. The reason why Big Ben was built is to keep London on time. And it used this universal time in order to keep time. Now this is where that zero meridian happens, latitudes, and Greenwich is the place where they were the keepers of time at that particular point. Universal time would equal GMT, Greenwich Mean Time. So the idea behind this is the scientists all got together and they figured out that by X amount of time, that's how many ticks are in a, each tick is a second, and they defined what a second was and so forth and so on. But everything was developed in Greenwich, England. If anybody ever gets a chance to go there, I highly suggest it. They do have tours. Next up, we have atomic time. Now, this is a timing standard in what we look at as, okay, I went from a mechanical device to now we have an atomic device. So our standard has changed to where now we use atomic time to keep the world's standard time. And you can go through and take a look at everything that through history. You can type in how do we keep time, I think, and it'll pull up a whole bunch of history on it. GMT, as they say, is still the world's time standard. We also give it different names. But it wasn't until 72, and believe it or not, I was alive during that time frame, that they started changing everything. They referred to atomic time now for its accuracy. That's about it. We still call it GMT. We call it Zulu for the military. We call it UTC, which is another name for it. So you're going to see these names are interchangeable for that zero meridian located in that general area, which goes from the top of the earth down to the bottom of the earth, from north to south. There are officially 24 different time zones. You'll notice that we have a link up there. I'm going to show you this link here real quick. We have different times. Now, another one they have is besides Z or zero meridian. That's another one, prime meridian. You got Zulu, which is us. And the idea is we always relate back to that UTC time or GMT time for referencing all of our missions. Now, when you get into a place where you have a clock that says Zulu time and then local time, because, you know, if you say, hey, at 1 o'clock our time, what's it going to be Zulu time? That's when the mission kicks off, not your local time. So you got to relate the two. So let me show you something here. I'm going to mute this and go to dateandtime.com and show you the time map. And I have no idea why it does this where it blacks out. Can't figure it out on my OBS here. So you look at the time map here. You'll see that we have 24 different time zones. But I want to point out some countries for you. Look at Australia. You notice something different in Australia? Can everybody see it? Let me ask you that. Oh, you cut out on me, Ian. Okay. What do you see different in Australia? Okay. Well, what's in the middle? Okay. Well, on your time zone maps, you can go and hit those dots and it'll tell you something about them when you put the cursor over it. I can't do it right this second. I just got the browser on it. In the middle, you'll notice that instead of a solid color, they have diagonal lines, don't they? Well, the reason why that is that way is they go with half hours. Another place that does it is India. Look at it. It's also got diagonal lines. Those are half hours. Now, do they still refer to GMT with everything? Yes, they do. They just have their own. Take a look at China. It covers almost 5 different time zones, but they only have one. But they still refer back to the UTC or GMT time when they're getting their time. So you can see that throughout, you know, our area, even in the United States, there's like we're on daylight savings time right now. So it makes a complete difference when you are, you know, thinking about, well, what is the time, you know, our time versus what Zulu time is, and you got to factor in the daylight savings time. There's places in the United States, I think New Mexico or Arizona doesn't observe it. There's places, there's cities that don't observe it. So you still have some latitude not to follow it, but you're still going to reference UTC for local time. So let's get back to the display here. I just wanted to point that out. We got others to show you. Timing sources. Okay, timing standards is what we reference everything to. Timing source is a completely unique thing. For example, if I tell you my time on my computer says 9:50, and I tell you to take a 10-minute break, you should be back by 10 o'clock by my time, not yours. But you're going to reference your clock to my clock. That is called, my clock would be the primary source, your clock will be the secondary source. And that's what this particular scenario, the timing source, is referenced. You want to go with the most accurate clock that you have as your primary source. We look at 2 different oscillators to generate time. We've got one that's quartz and the other one is atomic. The first one we look at, we have the least accurate. This uses a piezoelectric effect. Does anybody know what the piezoelectric effect is referenced to, or what does it do? Remember that back in Dolan Hall? I know you do, Sergeant Hoffler. How about you, Owen? Do you know? Well, that's not a bad way of going. You Google it, right? Okay, the piezoelectric effect. What does it do? Well, you're applying a voltage to something that's going to vibrate. Normally it's a quartz. I've seen a mica chip do it, and there's a couple other things that are out there that will vibrate to a certain frequency, and it uses that frequency as the reference for time. It can be temperature controlled and it can be aging. Those are the two problems that you have with the piezoelectric effect. Now, temperature can be controlled. Aging, you can't. That's the problem. Yeah, you can try to extend its life by using better products, but just like us, there's going to be a point where we're going to get really old and crap out, so to speak. We have atomic oscillators. We look at two of them called the rubidium and the cesium. Rubidium is the least accurate, and we just show you that this particular part where you have, this is how many clocks per second, this is how much it will drift compared to cesium, but you can see the difference between the two. That's what makes this so accurate. Is I've dealt with the rubidium in the 206 palette. How about you, Sergeant Hoffler? Have you dealt with either one? Oh, okay. Yeah, well, in the 206 palette, is a rubidium oscillator. And what you do is you get time and make sure that that time is accurate on that rubidium oscillator before you deploy. And when you deploy, you're using radios that deal with time, like frequency hopping. Remember in Block 3 that you were literally frequency hopping, and if you weren't on time with everybody else, it didn't work, did it? So that's the reason why we are using atomic oscillators. And also in the older versions of the GPS has rubidium and the newer versions have cesium, but they also come out with newer atomic oscillators that are more accurate than these. They're slowly but surely replacing them. We have something called time distribution and time coordination and distribution agencies. The first one that we referenced earlier, we talked about how many seconds or events are in the day, and that's how we're able to determine what time it is. Next up, we have three different agencies. We got BIPM, USNO, and NIST. So let me get right down to the BIPM portion. You can see we got a link down at the bottom. This is where time is kept. They not only do time itself, but they also keep other measurements there, like what's a kilogram, what's a centimeter, what's an inch, what's a mile, what's a kilometer, They keep all that time, and also weights and measures. The weights, if, like for example, in the United States, 1 pound may not equal 1 pound over in India. So you send them off to BIPM and they calibrate it for you and send it back. But that's when you're looking at something that's got to be so accurate. So let me show you BIPM site. It is a unique place. See what I mean about OBS? For some reason it likes to blank it out, but you can see this is the website. But I want you to take a look at the top left and you go, okay, why is it the acronym BIPM, but we say International Bureau of Weights and Measures, but on this website you can see that it says BIPM. It's French. That's the way they put it in line. Same thing that what we're discussing here. So you can go to this website. You'll see, if you peruse through it, you can see everything that's on there. Well, at least it's working for me. So let's get back to our display capture here. This is, again, if you wanted to look at this, you can come back to the recording and look at the timing on it, or you can just type in BIPM, BIPM.org. It'll take you there. This is where time is kept for the world. Primary frequency standard. The next one up is USNO. Pretty cool, this place. The headquarters is in Maryland. Where they keep time is in Pensacola. Kind of crazy. But anyway, you'll notice that we have a phone number down there too. So if you were to dial this phone number up, you're going to get not only UTC time, but you're going to get Eastern Standard Time. Again, I'm going to put up the USNO website. This is where you have to go. And it's relatively, it does have some history to it. So I suggest that you follow, take a look at that history. It's pretty cool when you go through the website. So, just, again, this is where the DOD references all of our time. Mm-hmm. Yeah. Oh, crap. Yeah, yeah. Well, my guess is I'm doing 60 frames per second versus that's probably about 20. So it'll probably coming over grainy. Thank you for... Oh, crap. Okay, so I ain't going to show the next one then, which is NIST. Thank you for letting me know. I was wondering why, because I'm looking at it going, man, I could barely see it in all my software, so I'd have to go back down in resolution then on those. I think I'll just do a screen capture and just have yeah. So it's, hey, improvement time. Yep. Good job. Thank you. Yeah. Oh, well, thank you. Appreciate it. You have a nice day, Sergeant Hoffler. All right, NIST, this is the civilian side. USNO is the military side. NIST is the civilian side. Now, what makes NIST so much more palatable for the military is you'll see that we have WWV, WWVH, WWVB. Let me explain those call signs. WWV is the headquarters in D.C. WWVH is Hawaii. That's that location. WWVB is Boulder, Colorado. You can hear it on 60 kilohertz. You can hear it on 2.5 megahertz, 5 megahertz, 10 megahertz, and 15 megahertz, as well as 20 megahertz. So if you were to take your HF radio and you're having problems trying to receive somebody, go to the time hacks here. Again, you can call this number. They will only broadcast UTC every 30 seconds, as opposed to USNO, which broadcasts it about every 10 seconds, and they alternate between the two. Again, NIST.gov, or just type in NIST, you should be able to get there. We have timing jitter. This is where our gaming scenarios start coming into play. The best way to explain excuse me, timing jitter is you guys have gone to YouTube many times, right? Just to see if you're playing the game correctly, or if you want to get a cheat or whatever in how to get to the next level. Correct me if I'm wrong at any point, right? Right? I know you guys, because I do it myself when I'm trying to go, how in the world do you play this map? So I'm with you. But anyway, as you are loading YouTube, every now and then you'll start to see that little circle. And you go, what? What's going on here? Especially with you guys dealing with, was it Boingo there in the dorms? So the easiest way to explain it is you got timing jitter. Now, you'll notice that when the video starts playing is when you have enough buffered. And we'll get to that in just a minute. And once it buffers enough, then the video will start playing. But it does look at that timing because it does not want to play the video if you don't have enough information in there to play it and it be steady along with the voice and the video. Because I've had some where the voice didn't match up with the video. We have short-term jitter. This is caused by, and this would be the best explanation for a YouTube video. It's because that something called an elastic store is that buffer. So what it's doing is it's gathering enough information, putting it in there, and if something goes wrong, it, like it didn't get all the information, at least the video will play at a consistent rate. Once it's removed, it's good to go. It'll go ahead and buffer all the way through. But long-term jitter, that's the biggest problems. This one is because you got two clocks. Yes, sir? Accidentally touched your mic? Yeah, that's okay. With timing jitter, with this long-term, if you don't use phase lock loop to get both of your times on, you got some problems. And that has everything to do with the clocks and how it goes down the line. Remember now, we're dealing with wires. We're not dealing with fiber yet, or most places of fiber. Fiber's quick, but it's still going to be a little bit off time. So the delays from wire to fiber, there's definitely a significant difference, but with those delays, you've got some timing issues. Normally it's in the milliseconds versus fiber, which is in the microseconds. And if you take a look at, there's a website, I want to say it's on the NIST side, you can actually see where there's a delay from UTC and they can calculate that delay, and it's normally in milliseconds. So just, peruse it, take a look at it, go through the history, especially NIST, because NIST was made up in World War II. And the reason why they moved to Boulder, Colorado is because of the possibility of, the Germans and the Japanese, shooting and taking out targets that were close to the coast. That's the reason why they moved the site to Boulder, Colorado. Figured it'd be in the middle of the world or middle of the United States and not have to worry about it too much. We have 4 different types of synchronization, network synchronization. They are plesiochronous. I like to call that the dinosaur. We have mutual, master clock, and master slave. First up is plesiochronous. With this one, they have nodes in each of the clock. The best way to describe this one is when you guys do an ad hoc where you get 2 computers that are talking to each other, whether it's via the cable or the internet or Bluetooth. That would be the easiest to say, because one computer may be off time. I've seen computers, because they didn't do their updates, I've seen them off at least a minute or 2. So it happens. And it happens. You may have an older computer and your, what do they call that? That CMOS battery may be on that last stage of keeping time and maybe getting slower. So there you have it. The easiest way I look at this is, you got 2 nodes, 2 computers talking to each other. And they classify this as using an elastic store. You have mutual. This one is, I like this particular diagram because it gives you an idea that what they're going to do is look at everybody's clocks and factor in the time. Now with this one is, if one of these fail, you don't have to worry about it because no big deal. They're still averaging time. We look at master clock. This one has a large amount of history to it, because if you go online, you'll find out master clock, and they reference Big Ben. Why Big Ben? Well, when it rang, it could be heard throughout the countryside. But the problem is, if Big Ben failed, everybody's clocks or watches or pocket watches that they had, they would go, oh crap, this is my time, and the other person could be off like a couple minutes. Especially trains back in the day. They used to look at the time that the train was on. So it just goes to show you that we have some history with this as far as master clock. We don't want to use this one because of the failure. If you take out the master clock, everybody fails. And I still remember my high school when the bells system that was, using time, it failed. So literally we would not get the same time to, change classes. They would have to come over the internet, or not internet, the intercom, and let us know, hey, it's time to change. Okay, everybody should be in their class, that type deal, for about 2 weeks before they got that figured out. The last one is called master slave. This has been in service for probably since the 1950s, and the idea behind master slave is if you got plenty of hard drives, because it was related to hard drives, you would have to pull a jumper out of the rear. So if you put 2 hard drives in, one hard drive would be the master, the second one would be the slave. If the master failed, the slave would take over. So we use this in what they call DOD or DCS because of the high degree of survivability, because we have layers upon layers as to who could take over the main time. And that's what you have. You have purpose of timing, time standards, timing sources, time coordination, distribution agencies, timing jitter, and network synchronization. Any questions on that? I know I went through it pretty doggone fast, but, oh, hi Airman Corden, how you doing? You can type in chat. Airman Corden? Ah, okay, good. Typing. Well, you are forgiven for this time, but let me talk to you after class, okay? Did you just get assigned to this? Okay, that could be part of the problem. Did you not have a class number? Okay, so you got yesterday. Were you assigned a class number? And if so, what time were you given that? So now you have 8 in class. And while he's typing, I'm going to go on to the next one. Okay. Well, that could be the reason why you didn't know. Okay. We'll still talk after class so we can take care of it. It looks like you're assigned to 2-6 now, because that's what's by your name there. Okay, next up, let's go to Objective 1 Bravo. Identify a basic or relationship of basic facts, state general principles associated with principles, capabilities, and limitations of multiplexers. All right. As you well know, you're going to be dealing with multiplexers. In fact, tomorrow you're going to be dealing with what's called the NSM-50, Nodal Satellite. Go ahead. Oh yeah, that's right. Today's Friday. It's one of those I still can't get days. They're just a blur to me right now. So yes, Monday. Sorry about that. Good catch. So Monday, you're going to be dealing with an NSM-50. We're going to go over the information later on this afternoon. So the idea behind the NSM is right behind the next bunch of slides, And you're going to see everything that we talked about. Most of it's going to be in the NSM. So let's go. Okay, I got somebody, Myth Writer. Who's Myth Writer? Okay. Thursday from 12 till they finish. What's that one? Okay. All right. Okay. All right. And yeah. Airman Yang, I'm looking at the schedule. Okay. Did they give you a like Thursday? Which one is it? Is it a practice, day 3, day? Okay. When he said Thursday, correct there, Wheeler, right? Okay. Are we in lab or are we telework? Because it's really... Okay. All right. So that particular day, we may have to do a workaround on Thursday. It just depends what class I've got coming in and going out, because I'm supposed to be handling all the classes for Block 7 right now. So I don't know what kind of help I've got for next week. I got help today, but I don't know if I'm going to have help next week. I will know, and we'll work around that. But thank you for sending that to me. All right. Thank you. And let's get to the next one. We have general multiplexing terms, input data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, analog to digital conversion. This is where the rubber hits the pavement, so to speak. These are terms. And when I look at analog and digital, you can use either one of them. And I like to say, use one of these as your source or for understanding, and whatever you choose, it will be the opposite of the next definition. So if you're to choose digital, you can see it says limited number of values. It's discrete or finite. Those are 3 words I like to use with digital. What's analog? The opposite of those words. So it would be unlimited, infinite, and indiscrete. So it just gives you an idea how you can try to remember these. Next up, we have bit, not to be confused with byte. Byte is logic 1s or 0s. It's 1 bit. We make, we could use 8-bit words. That would be a possible byte. And if you look it up on Google, you'll find out the differences between bit and byte relationships. And it's kind of crazy because byte's going to be smaller than bits. Multiplexing. This is a term that is used combining 2 or more users. Now, the reason why they put channels in there is because if you only have 1 user, then you have 1 channel. The problem with users is it could be more than 1. You got multiple users in a channel. You may have 24 channels, but you may have a couple hundred users. So you see the complexity of that. Just remember, it is an aggregate signal coming in or going out of the multiplexer. And it can be any one of these: analog, digital, voice, data, audio, you name it. But it is a digital format. So this gives you an idea how the multiplexer is going to take these channels, which is user inputs. And number 1 shows you a diagonal line, number 2 is a solid bar, the next one's a horizontal line, and you can see each one of them are put together. Channels 1, 2, and 3, 1, 2, 3, 1, 2, 3, and sent out in an aggregate form. Next up, we have sampling. This is where we are going to take a sample of that analog signal, and in that one period, that sample is going to be in equal slices. It will be sequentially, so we don't get it out of sequence. And that is considered sampling, not to be confused with going to the buffet and sampling all the food there. Just not cool. You get fat that way. Next up, we have frame. This is a sample from each channel that gives us one frame. You can see frame 1 shows you a sample of each of the channels. Frame 2, same thing. And again, this is all sequentially laid out. We have non-informational bits. The reason why we have non-informational bits is because we have an 8-bit word, but we got to tell that word what to do. Now, you have a frame bit, that's a sample, but it's not part of that word, not the intelligence. You have a stop and start bit because of that word. You got the front end of the word to the back end of the word. You sometimes need to tell the computer where to stop and where to start. And then, of course, when you're in particular synchronization portions, they're going to cram it full of stuffing bits. And that's to make it going from an asynchronous to a synchronous style. We'll get into that in just a minute. Bandwidth can mean a couple things. How fast? What's the size? What's the frequency range? All of those. So it depends on what it is talking about versus, you know, if you're talking about a frequency range for your bandwidth versus how fast the data is going. So try to figure out what it's asking before you apply those definitions to it. So you got asynchronous. This one is a flexible type style. Keyboards and mouse. Your computer pretty much uses it when you're talking to the multiplexer or, you know, your router or whatever. Synchronous, this one is a little bit different. Like if you had cameras and you needed to see all of these cameras, and of course your screen is big enough to handle all the cameras, that's what synchronous is there for, because you're using every bit of that bandwidth in order to see it. So this one will be, you know, here's frame 1, channels 1 through blah, 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 and so forth and so on. You're not wasting any bandwidth, but if you were to apply that to computer usage, there's going to be times where you're not going to be on, and then you're going to waste that bandwidth. Just like if one of the cameras fails, you're wasting that bandwidth on there. Then you have something called isochronous. Isochronous is something called async at a synchronous rate. In other words, your stop and start bits are going to be in there. The 8-bit word's going to be in there. But the biggest thing is if you don't have anything to put in there, you still have to sync it up, and the way they do it is adding stuffing bits in there. Not the kind that you put in turkeys, but you get the point. You need to fill up that cavity with something, so you put stuffing in it. Same thing for isochronous. So the idea is we're at a synchronous rate, but we still have stop and start bits to tell the distant end where to begin and where to end, but it should have some information in it. If it doesn't, then you got to fill it up with something. Next up, we have something called FDM, called frequency division multiplexing. This one is going to assign frequencies in what we do. Now, with this one, I equate it to the old cell sites where the phones would scan what frequency was available before you could dial out. The problem with this is if when you went from one cell site to the other and you were, let's just say, on user A at 82 to 83, and you went from that cell site and got handed off to the other cell site, well, if someone was on 82 to 83, you got bumped or dropped. Now we go into a little bit different scenario where we have TDM. Now this one is broadcast all on one channel. It's still doing the same thing. The difference is we're looking for timing slots. Now, obviously, if one cell site is completely full, the chances of you being dropped when you get to it are pretty good, but it's a very unusual occurrence with it. I've only been dropped, over the last 5 to 10 years, probably one time. Why? Because being out on the road, you may be talking to your significant other or your relatives and you go from one cell site to the other, especially when it gets into the city, you could get dropped. And this gives you an idea about a TDM. You can see that we have users, interleaves all samples. That's a key word there later on down the line. Before transmitting this to the dissonant. Now you can see with the frame we have channels 1 through 4. That's for frame 1, frame 2 is 1 through 4, and so forth and so on. We have modes of TDM, and we only focus on synchronous and asynchronous, but this is more of describing what they do. You can assign time slots to all the channels, whether it's active or not. We use frame bits to show you where everything is, but the problem is if there's nothing to put in that channel, it's wasted bandwidth. Whoops. Here gives you an idea of this wasted bandwidth, especially when you get to frame 2, 3, and 4. You can see that we have data all the way from 1 to 4 with channel 1. Channel 2 only has 2 bits, channel 3 only has 1 bit, and channel 4 only has 3. So you can see that if we didn't have anything in there, we're wasting bandwidth. With async, and this is the relationship that you guys have with Boingo, it's a flexible thing. So if you get on late at night, let's just say 1, 2 o'clock in the morning to play a game online, you're probably going to have enough bandwidth to do it. If you got on at like we're doing now, let's say in the afternoon about 4 o'clock, everybody's getting on, and you're going to have to wait for your time to get on. So that's the reason why you have all this lag time with it, and you can't play a game whatsoever. But if you're off, do I have anybody that is off the base here? No? Okay. All right. If you're off the base, and have your own internet provider, the chances of you having to wait for your time is pretty slim. On the base, especially around that 4 o'clock, 5 o'clock time frame, you're going to have to wait for your time. That's a lot of people trying to get onto that multiplexer. With async, you can see that, you can see that frame 1, everybody's online, everybody's having to wait for their time. Frame 2, all of a sudden the stuff starts getting faster and faster when you get to frame 4. So basically what you're seeing is time increases for you to get on without any delay versus frame 1. So the wealth of information at 4 or 5 o'clock in the afternoon versus 1 o'clock in the night, there's frame 4. So you can play your games online during that time frame. Why would you be up that late anyway? Because most of the good players are already in bed. You have async. You can see that it gives you an idea. You have a frame bit to start with everything on frame 1. You got a start and a stop bit for your 8 bits of intelligence. This is called overhead. Now, I'm not sure if they discussed this in Block 6, but overhead is all the stuff that is needed to sync things up and keep everything in a sequential manner. Did they say anything about that in Block 6? Okay, so your stop and start bits, your framing bits are called overhead. When you get into isochronous, and this is where that FCC came in, FCC 100 came into place, is isochronous is what we call a bandwidth hog. It's got a lot of information on it, non-information versus information or intelligence. And that's the reason why a lot of the, I want to say, the Air Force is not going to, is that isochronous. The only thing I can think of for isochronous might be a scenario is if you're in the WSA, which is weapons storage area, and you're using alarms and video to look out and see what's going on. That's the only thing I can think of that ISO would be used for. Next up, we have shown you that when we do not have any information to be put in this case in frame 2, we're missing, I think it's Charlie. Yeah, Charlie in there. You got to stuff it. And that's the reason why isochronous is such a big hog when it comes to bandwidth. Because if there's no information in there, let's just say a camera went out, well, there's no information, but you got to have a placeholder. So that's where the stuffing comes into play. And it's, like I said, it keeps wasting bandwidth. It's great when it works because it's always consistent, but it's awful when it isn't. Demultiplexing. If you do this in multiplexing, you got to do it in demultiplexing. That's the biggest thing about having multiplexing versus demultiplexing. And again, if you have an encryption when you send the stuff out and you don't have encryption when you get the stuff back in, then why are you doing it? Okay? That's the biggest thing. It's also a troubleshooting hint. If you're encrypting everything going out but nothing's getting decrypted coming back in, maybe you might have a problem with your encryption device. So that's a troubleshooting point. Signaling formats. This is where things get a little hairy. We have non-return to zero, and conditioned die phase. Every one of these can be researched on Google. However, conditioned die phase is a little difficult to find. It will call it Manchester die phase, which is an older version of CDI. I'm beginning to think that the military developed this quote-unquote conditioned die phase, even though it's pretty close to Manchester die phase. When you look at this number, do you read it from left to right or right to left? Let's ask, don't say anything, Gordon. Owen, what do you think? Peebles? Warnke? Okay. Yan? Jurassics? Matzak? And Wheeler. You sure? Get the point? Okay. The reason why I point this out is everybody has the habit of going from left to right because that's the way they read it. But when you look at numbers, it's always from right to left. Now, we don't get it. I mean, as instructors, we're human beings too. We always want to start from the left and go to the right. But when it comes to numbers, it should always be from right to left. And that's how everything is written. When you are in block 1 and you're looking at an O-scope, and I bet you probably didn't clue this in, but everything, when you're trying to sync up everything, it always wants to go from left, from right to left. Look at it one of these times. Most O-scopes I've had to deal with always want to go from right to left, and that's the way things work. So with that in mind, we also do digital the same way. We always want to start our clock pulses, which is at the bottom. Those are what the up and down digital sequence there, from right to left. You always want to develop your words from right to left, and that's how we are supposed to do it. Now, probably in Dolan Hall, they always went from left to right, didn't they? Well, that's really not how it's supposed to be done. And we try to be consistent with this to get you guys in the practice of doing it correctly. When we look at non-return to zero, we're looking at the namesake. What does it mean, non-return to zero? Well, the biggest thing is that second sentence does not return to zero halfway through the clock cycle. Okay, we're going to show you what happens here. But I do want to point to that first sentence is the most common format of data within the multiplexer. Let me try to explain it to you in a picture with words. If you have a multiplexer and you have 24 channels coming into it, those 24 channels will be different signaling formats depending on the device that's doing it. When it gets inside the multiplexer, there's an oscillator in there. It's going to keep the computers that were, let's say, out of sync in sync. You know, bye bye bye, in sync, bye bye bye. No, boy band in sync. Okay. Look it up on YouTube. But anyway, I digress. With that in mind, the oscillators sync up everything and change it to the data, which is called NRZ, internally of the multiplexer. So therefore, everything is synced up, formed into an aggregate, synced up again, and sent to the dissonant. When it gets to the other multiplexer, that data normally, and I've seen this where it's either NRZ or CDI, it's going to take that data, convert it into NRZ regardless of what it is after it syncs it up, then change the NRZ to whatever the user is on that dissonant. So you can see within the multiplexers, they're always wanting it to be NRZ regardless of the signaling format either going out or coming in. Two types that we look at is neutral and polar. Let me explain neutral. Neutral is always from 0 to 5 volts. So the 0 is always 0 and the plus 5 is a logic of 1. So logic 0 is 0, logic 1 is plus 5. The problem with this is you can only run short cables. You're going to need a clock cycle to be sent along with it to make sure it is in time. RZ neutral, you can see we have plus 5 volts and 0. Starting from the left, we have a 0 piece of data. Excuse me, not left, from right to left. You're going to see we have a clock cycle above it. We always want to start going with our clock cycles from the neutral or 0 site, going to the plus side, and then coming back down to 0 within that one clock cycle. That's where our data is. So you can see that as this NRZ pulse is coming in here, we're looking at the data in how we change the signaling format. So the data is telling me I'm going to be 0, so I'm going to stay at the 0 line all the way through the clock cycle. From, again, right to left, we see a 1. We go halfway through the clock cycle and then go back down to 0. That's on that clock cycle. But we do not change because the name says we don't have to. We have another data of 1. And it stays the plus 5 volts for that logic of 1. Here comes a 0. We're going to go down to the 0 and we're going to stay there. And you can see we have 3 zeros in a row, and then a 1, then a 0, and then a 1, and a 0. Let me explain the short cable lengths. As you well know, that the longer the length, the more capacitance and inductance it gathers and makes it resistive. So when your signal goes out further and further, instead of having a 0 to 5 volt difference, you may have a +1, 2, +3, and at the distant end, it's going to be really hard to differentiate what's a 1 and what's a 0. It's the reason why they don't run long cables with NRZ neutral. When we get to polar, though, there's a 10 volt difference. But our ones are either a +5 or -5. Oh, excuse me, our +5, our zeros are a -5. Again, the NRZ, non-return to 0, does not play an important factor in there. It is not self-clocking, which means that I have to send a clock cycle along with the signaling format. We go through the waveform. We're keeping the same data from right to left. You can see with the clock cycle, every clock cycle happens, it stays at that state. So the 0 data is at a -5. We go to a 1, it goes to a +5. We have another 1, we still stay at +5. We don't return to 0 at any point in this waveform when we apply the data. Again, NRZ needs a clock cycle to be sent with the signaling format. We have something called return to 0. This one means that, hey, if I'm at a +5 or -5, I'm going to return to 0 halfway through the clock cycle. There are 4 different types: neutral, polar, bipolar, and bipolar with zero suppression. When we get into bipolar, you're going to see NRZ and RZ bipolar and RZ bipolar with zero suppression in the NSN. So let's take a look at these. First of all, neutral. You got a +5 for a 1 and a 0 for our logic 0. It is not self-clocking. Again, it's a short cable. You can see, though, we start to see where the clocks play a very important part with this particular signaling format. The NRZ, we see a clock we see the clock, we see the data, which is 0, again, starting from the right, going to the left. A 0 means we're staying at 0. With a data of 1, we immediately go to the +5, but halfway through the clock cycle, look what happens. We go back down to 0. And again, on number 1, we're doing that too. 0 stays at 0 until we get to another 1 and back up to +5. Halfway through the clock cycle, we go down again. We see a 0, it stays 0. Here comes a 1, voila, we do it again. Go to +5, and then halfway through the clock cycle, we go down. Problem with this one is it doesn't look anything close to that clock cycle, even though the 1s are making things happen halfway through the clock cycle. We look at RZ polar. This one's a little bit different. You can see the logic of 1 is a +5 and the logic of 0 is a -5. This one is self-clocking. Let's take a look. RZ polar waveform, you got the clock cycle, you got the data. Starting from right to left, you have a 0 data. The first place it's going to go is a -5. Halfway through the clock cycle, it's doing something this time. It's going back to 0. You have a 1, this one goes to the +5. Halfway through the clock cycle, it goes down. We hit the 1 again for the data, and we clock to the +5, and then back down halfway through the clock cycle. So every time the clock cycle does something, we're going to return back to 0. This one is self-clocking. No problems or no questions asked on this one. So it doesn't matter what it's doing halfway through the clock cycle, it automatically knows it's doing something going back to 0. So this is the first one that we're going over that is self-clocking. You don't need to send the extra data to the distant, which is the clock cycle and the signaling format. We get the bipolar. It looks almost similar to RZ polar, except the ones are flip-flopping between a +5 and the -5, hence the word bipolar. Logic ones are always going to be 0. This one is not self-clocking. So let me stop here and explain something about RZ bipolar. There's another name for it. It's called alternate mark inversion, AMI. You're going to see both of these, where it says RZ bipolar, and you will see AMI, Alpha Mike India, in the NSM tech order, or tech manual, excuse me. Please pay heed to it, because everything we're telling you now that we're leading up to this part, okay, is a signaling format that you're going to see. So I'll wait for him to come back. In fact, does anybody else have to go? You want to take a quick 5-minute break? You know what, I'll call it. Let's take a 5-minute break. Be back at, my clock says 10:43. Be back at 10:48. All right? Break. All right. Mute your mics.
You've taught this clock before, haven't you?
Yeah.
Big Ben and self-clocking. I've heard all this before, hon.
Yeah. And it doesn't get old for me. Well, the difference is normally I teach this thing about 4 or 5 times, and then they'll put me in a different block where I'm not having to do it all the time.
I didn't want to send the receipt that it came with because it seems tacky. $50. That was a lot, huh? You didn't have to do that much. But anyway.
You said 50.
25, but that's fine. See, this one, in case they can't scan it or something with the actual card, you know, they say this to, you know, and this one just has that thing and that thing. It doesn't say.
I forgot.
I
didn't even
think
think
of
about
it
putting
either.
it as a
No,
gift.
I didn't think of it.
Yeah.
It's fine.
All right. Really, baby? Teddy, get off of there.
That's his bed.
Yeah, that's true. I'm getting ready to go live again. Okay. Everybody back? Let's go through the list. I got a minute. All right. So I see Cordon's back. Owen, back? Owen, are you back yet? You can type in chat. Peoples? Warnke? And Yan, I thought I heard you. Jurassics? Matzak? Guess he's not back yet. Wheeler? Okay, so we're waiting on Owen and Matzak. Oh, you're back? Okay, good. Okay, good. Good. All right, so we have RZ bipolar. Again, this can be made self-clocking with zero suppression. So right now we're going to look at RZ bipolar, and then we're going to look at one called RZ bipolar zero suppression. So let's take a look at each one of them. RZ bipolar, you can see that with the datas of 1, they flip-flop, hence the word bipolar, or alternate mark inversion. The difficulty is when you have a string of zeros, it doesn't know anything and what to do. Because it's not doing anything within those zeros, it can't sync up. So you do need to send a clock cycle with this particular waveform. With RZ bipolar zero suppression, there is a number, and you can see this on, actually I have some numbers down here. You're going to see things like Bravo 8 Zulu Sierra, which is bipolar number 8 with zero suppression. It means it's going to throw a bit violation at the 9th zero. This is North American, by the way. It's also a T1 line, and there's other lines like T2 has B6, T3 is a B3, and those are throwing bit violations on the 7th zero or the 3rd zero. Now you don't have to remember these. You just need to know that when we have bipolar with zero suppression, it's self-clocking. So we're just trying to show you how it's self-clocking and also give you the relationship of this signaling format being in the NSM tech manual. So you are going to have a hands-on approach with the bipolar with zero suppression and bipolar, because I think the T1 is bipolar, the E1 is bipolar with zero suppression. So with bit violations, what it's telling you is when we have a succession of zeros in a row, we're going to throw a bit violation on that zero that it dictates. With that zero, excuse me for just a second. Sorry about that. With that zero, That bit violation is going to look back down to the distant end, whatever the last bipolar signal was for a data of 1, and it's going to emulate it. So let's take a look at what we're talking about here. Okay, again, starting from right to left, we see the data of 0. The next one is a data of 1. Now this one goes, and we always try to start with the positive side before we go to the negative side. Sometimes it doesn't happen, but that's normally our reaction to how we start things off. So with the 1, halfway through the clock cycle, the first part will be a +5. It's going to go return to 0, hence the name bipolar with zero suppression, return to 0. The next data of a 1 is going to flip-flop, hence the word bipolar. We hit 3 zeros in a row, and on the 4th 0, we're going to see a bit violation because you've told it to do that. If there's 3 zeros in a row, if there's a 4th 0, you're going to throw a bit violation. With that bit violation, it's going to look back at the last 1 and emulate it. In other words, copy it. Since it was going into the -5, it's going to do the same thing. Now the distant end says, oh, I got a problem here because there's more zeros in a row, so I know that this is a bit violation, and that number is a 0. So now I can sync everything back up, and that's the reason why it's self-clocking. So now we have two signaling formats that are self-clocking, and we're showing you this. What's the first one there, Matt, Zach? Do you know? Do you remember? What's the first self-clocking mode that we've looked at? How about you, Wheeler? You know? Peebles? No. Nope. Now you're starting to weed it out. Okay. Gentlemen, NRZ are not self-clocking. It's when we get into the RZ that there are 2 signaling formats that are self-clocking. One of them is RZ polar. You were close, but you're still saying NRZ. So NRZ, you have to send a clock cycle with it because it is not self-clocking. RZ polar is self-clocking. You don't need to send an extra piece of information down the line. The next one is RZ bipolar zero suppression is self-clocking. And this gives you the idea that how it is self-clocking. We go back up to RZ polar and you can see that it is self-clocking. RZ bipolar, you need to tell it how to self-clock. Which leads us to conditioned diphase. Now with conditioned diphase, it's a lot different than all the other signaling formats because it doesn't rely on a +5 or a 0. It relies on transitions. With a logic 1, there's only one transition within the clock cycle. With a logic 0, there are 2. Now, you'll notice the sentence underneath them, it says out of phase with the clock during some clock cycles. That's with logic of 1. So it doesn't matter as long as they get one clock cycle or one transition in a clock cycle. So it can be off just a little bit. Whereas the zeros are normally in phase with the clock, and that's how it's self-clocking. So there are 3 signaling formats now that we've gone over that are self-clocking. You have RZ polar, RZ bipolar zero suppression, and CDI. So let's take a look at the waveform that we've got generated for you. Again, we're looking at the clock. You have the clock pulse, same thing, clock cycle, with a data of 0. 0 means there are 2 transitions, so you can see that it's in phase with the clock cycle. With a 1, it can be anywhere in that clock cycle. So how does it figure out the dis and in? Well, when you see zeros, that's when you see 2 clock cycles, and it's in sync with the way it was sent. So CDI relies on transitions. The others rely on voltages to determine whether or not it's a logic of 1 or if it's a logic of 0. We have something called Nyquist theorem. And I'm going to stop there because it's getting close to lunchtime, and then we're going to pick this up and continue all the way through 2 alpha at the 1 o'clock string. Does everybody agree with that? Sure you do. You guys are hungry, right? So meet back here, 1 o'clock, and we'll continue on with the Nyquist theorem. Okay? All right, we'll see you then. I'm sorry, you faded out at the last part there.